Hi there, my name is Brian Worthmann, and I'm in the Applied Physics PhD program here at the University of Michigan, and I'm studying underwater acoustics. So I assume if you clicked on this video, you're probably interested in what my research is all about. I'm also going to guess that you're probably not an expert in underwater acoustics, since statistically speaking, the vast majority of people in the world are not. But nevertheless, I hope to share some of my work with you. Will you walk away an acoustics expert? Probably not. But will you walk away thinking, I never thought about that before? I hope so. So to get started, I want you to picture the ocean. What do you see? Personally, I'm picturing the beach. Warm sun, sand, gentle waves. Really just a pretty relaxing scene. Now, picture what it's like under the ocean. You might expect an equally peaceful place, perhaps something beautiful like Atlantica from The Little Mermaid, or maybe something exotic and mysterious like the lost city of Atlantis, or maybe even the adrenaline-pumping East Australian Current, or the EAC for all you Finding Nemo fans. As you might already guess, Disney didn't quite capture what the real ocean's like. The real ocean is a much more sinister sounding place. For starters, it's deep, really deep. The ocean is, on average, just over 2 miles deep. To put that in perspective, that's about the height at which parachuters jump out of planes. And keep in mind, that's just the average. The maximum depth is almost triple that. Additionally, the ocean's really dark. It's like being in a super thick fog. You can only see maybe 30 feet in front of you on a good day in most parts of the ocean. Plus, the ocean strongly absorbs most of the light from the sun. The lower 95% is so dark, photosynthesis can't even occur. And finally, it's cold. The average ocean temperature is only a few degrees above freezing, meaning that if you were submerged in it, that you would literally freeze to death in half an hour. So again, the ocean's deep, dark, and cold. Not quite what Disney led us to believe. Well, thankfully, most of us can live our daily lives on land and never have to deal with the harsh realities of the ocean. But for some people in the world, they must deal with these difficulties every day. There are many such people in the world, but I want to focus on one example: submarine captains. So, for the sake of discussion, let's suppose that we're submarine captains, and our job is to find enemy submarines before they find us. So how do we go about finding them? If we were on land, we'd be able to see for miles, and we'd have all the benefits that come with GPS and radar, satellite imagery, and cell phone service. But underwater, all these options go straight out the window. Heck, we can only see a few yards in front of us, and yet somehow we gotta try and find a submarine. So what do? Well, we can't just say, I don't know, and quit, because if we did that, the Cold War may very well have been called World War III. So, considering the potential gravity of the situation, we better try harder. But try as we might, we're never going to be able to overcome the physical limitations of light underwater. However, we can get around this problem by instead using sound. So as you may already know, sound travels underwater. After all, where do you think those beautiful whale sounds and those high-pitched dolphin clicks come from? But there's something very surprising about sound underwater. It travels really far, a lot farther than we're used to in air. Consider the following. If there was a rock concert playing outdoors, it would sound like a very quiet whisper about 4 miles away. However, the same rock concert playing underwater could be heard almost 1,300 miles away, or about the distance from Maine to Florida. So, like I said, very, very far. Now, I want to be clear. I'm not suggesting that you start a new underwater rock band and have people listen thousands of miles away by sticking their ears in the water. The human ears and voice were not made to work well underwater, and as a result, even though sound travels a lot farther underwater, we can't necessarily be as loud or hear as well underwater. However, speakers that are specifically designed for working underwater can be loud, or other things can be unintentionally loud underwater, like a submarine with its engine running. So let's return to the problem of finding a submarine. We've already discussed how we can't see very far underwater, but that we can hear pretty far underwater. So, if we're clever with the use of microphones underwater, which by the way are called hydrophones, then we can use sound to sort of see underwater. This process is called sonar, and it was invented during World War I, but it became a lot more important during World War II and the Cold War. Generally speaking, there are two types of sonar: active and passive. Active means you make a sound and listen for the return. While the technical aspects are of course complicated, the general principle is straightforward. You make a sound, and you time how long it takes to hear an echo, and then, with the speed of sound, you calculate a distance. This is exactly how fish finders and depth finders work. The less intuitive type of sonar is passive. In this case, all you do is listen. You simply record what you hear and try and get as much information as humanly possible out of that sound. This problem of getting information from a recording is part of a more general class of problems called remote sensing. Broadly speaking, there are 4 levels of remote sensing. First, detection, which asks the question, was that just noise or was that something else? Second, classification. Okay, so you heard something, but was it something important? Was that a submarine or a whale? And if it was something important, then you move to step 3, localization. This says, okay, we know that what we heard was important, but where did it come from? More importantly, did the sound come from right behind us, or did that sound originate several miles away? Finally, the last step, identification. This asks the very specific question of who or what made that sound. For example, was it a friendly submarine or an enemy one? My research deals with that third step, localization. How do we use the sound that we recorded, along with any and all information we have about the nearby ocean environment, to ultimately back out the location of the sound source? This may sound, pun intended, like a tough question. After all, how do we take recordings of propeller noise and turn that into a geographical coordinate in the ocean? But, in fact, you already encounter a very similar type of localization problem every day, and solve it without even thinking about it. So for this part, it would be great if you were listening with headphones on, so just pause the video and go get them. By the way, if you're using earbuds, make sure that you have the left and the right earbuds in the correct spots. Look for the little L and the little R written on the sides. Alright, so now, put them in, and listen to the following. Okay, I know that sound is annoying, but where did that sound come from? I'd say it probably sounds like it's coming from straight ahead, or from above my head. Okay, now, listen to this. That one sounds like it came from the left, doesn't it? Now, try this one. That one sounds like it came from the right, didn't it? So how'd I do that? You might think I'd turn the sound on in only one headphone, but I didn't. Try rewinding and listening with only one earbud in. You'll hear the exact same thing in each ear. But when listened together, they sound like they have a direction. How is that possible? So, what I did was, I slightly changed the timing of the sound in your ears. So slight that it was under 1 millisecond, which is about how long it takes sound to travel the width of the human head. To appreciate how fast this is, a blink of an eye is a few hundred milliseconds. In fact, it takes a neuron about a millisecond to fire, so this time delay is literally faster than you can think. So by changing the timing of sound arriving in your ear, your brain interpreted that as sound coming from the left or the right, depending on the size of the delay. Isn't it amazing that your brain can do that, even though the timescales are so much faster than you can even see or think? Anyway, going back to Sonar, essentially sonar systems are more elaborate digital versions of your ears and brain. They work by recording sound at several different locations and listening to the time delays. From this, they can determine arrival angles. The process gets even more complicated in the ocean because sound can get from point A to point B in more than one way. If you have some source of sound in the ocean, let's say here, and you're listening over here, the sound can get there in a straight line, but it can also bounce off the surface like a mirror or reflect off the bottom. The result is that one source essentially sounds like several echoes, often overlapping. Our ears would be very confused by these sounds, but computers with the right algorithms can handle it. They use information about the timing and the angle of those echoes to ultimately determine where a sound must have come from in the ocean. My job is to use a combination of math, physics, and engineering to design such algorithms to make sonar localization better, faster, and more robust. And so far, it's been going pretty well. So hopefully, you've learned a little bit about my field of underwater acoustics. To summarize, the ocean's a really deep, dark, cold place. However, we can use sound to essentially see underwater. This process, known as sonar, is very much like the way your ears already figure out which direction a sound came from. What I do is work on ways to get computer algorithms to do a similar job in the much more complicated ocean environment. This research has obvious national defense implications, but, as it turns out, the math and physics are easily carried over to other fields, which could be as diverse as biomedical ultrasound, oil exploration, structural health monitoring, or marine biology. I'm Brian Worthmann, and I thank you very much for listening.